Good morning to everyone. My name is Jennifer Molina. I am a PhD student in the Bioelectronics section at Simvestab in Mexico, and I'm going to present our work entitled Portable Olfactometric Platform for SENT classification. The content of the presentation is composed of introduction, objective materials and methodology, results and discussion, conclusions, references, and at the end I will give you the contact information of the authors. In the introduction, I will give you the motivation of this work. In the food industry, it is common to carry out tasks such as quality control, product qualification, classification by origin, and detection of subcomponents. For such purposes, it's common that analytical techniques such as gas chromatography or mass spectrometry are used. However, such techniques have certain disadvantages such as high operating cost, complicated detection methods, complicated sample preparation, and long response times. On the other hand, the sense of smell has been used as a quality indicator by the industry based on the human experience of rejecting or approving a product according to its smell, giving rise to the development of artificial olfactory systems. An alternative to traditional methods is the use of bioinspired techniques and systems such as olfactometry and the electronic noses, which are the main topics of this work, of which I will speak now. Firstly, olfactometry involves a set of techniques that help us to evaluate the sense of smell. This leads the use of olfactometers, which are instruments to measure the sensitivity of the sense of smell concerning intensity, concentration, and quality of an odor. This presents a characteristic that is the impossibility of objectively evaluating the characteristic of the olfactory stimulus to be analyzed. So an alternative to this disadvantage is the inclusion of an electronic nose. In second place are the electronic noses, which are instruments that emulate the sense of smell of mammals and insects. Therefore, they recognize odors by relating concentrations to a specific odor, and they are generally composed of an array of gas sensors and a pattern recognition system such as artificial neural networks. The combination of these two techniques offers the opportunity to integrate a platform for the analysis of odorants, including a stimulation stage with an objective evaluation stage of the stimulus. There are very few works that combine these two techniques, so this paper is focused on this combination for analyze these samples. And to finish the introduction, why tea? Well, tea is one of the beverages with the highest consumption at worldwide, since it is easily and economically accessible. It is of interest to analyze and classify it using the bioinspired techniques employed in this work. The main objective of this work was classify a set of the samples by analyzing the response of an array of metal oxide gas sensors to a controlled stimulus using an olfactometric platform designed in our laboratory consisting in a controlled flow olfactometer and an electronic nose. Materials and methodology. The samples to be analyzed were taken of bags from 18 types of tea of 4 different brands. Regarding the instrumentation, the developed olfactometric platform was used, which is composed of an olfactometer and an electronic nose. The olfactometer used produces a controlled all-odor stimulus. The stimulus is generated by controlling the pressure inside the container where the sample to be analyzed is placed. The electronic nose is made of an array of 6 metal oxide gas sensors with different specificity. And these are the sensors used. And after signal acquisition, principal component analysis was applied to observe the dispersion of data, characteristic selection, and dimension reduction. Artificial neural network of type multilayer perceptron was used to build a classification model. As per the methodology, it is divided into parts. The first one refers to the sequence of the record of samples. First, sample placement. A 1.2 grams tea bag was placed in the olfactometric glass container. Then there is the generation of the stimulus, an airflow which goes from the container to the electronic node sensor array was generated, and the stimulation cycle lasts 700 seconds, and it is repeated 9 times per sample. This is an example of the distribution of the stimulus response of one of the sensors. And after stimulation, the sensor array detects samples odor and produces a response. Here we can observe the response of the 6 sensors to one of the samples. And finally, the response recording was made. The sensor array signals are stored by an acquisition system at the sample rate of 5 samples per second. And the second part of the methodology regards to the sequence of signal processing. First, signal preprocessing is made. After signal acquisition, a 5-sample moving average filter was applied to obtain data of the 6 sensors that were concatenated. And here we can observe graphically this concatenation. And the signal processing. Principal component analysis was applied to observe the dispersion of data, characteristic selection, and dimension reduction. The first 5 components of each record were taken from the obtained data matrix, and these components confirmed the characteristic vectors for each sample. And classification model. Different artificial neural networks of multilayer perceptron type were used to build classification models. The optimal one was used to classify the samples. And finally, the test model. Keyfold cross-validation was applied for validation of artificial neural network model, repeating the test 100 times, and the training was performed with 66% of data. The rest of data was used to test the model. The proposed classification model clusters the tea samples by common ingredients, having 6 classes: citric, sweet fruity, chamomile, green tea, black tea, lemongrass, and hibiscus tea scent. Here we look how the information was modeled. For the classification model, a multilayer perceptron was used with 5 neurons in the input layer, 18 neurons in the hidden layer with tangent signal transfer function, and 6 neurons in the output layer with logarithmic sigmoid transfer function. The training protocol was Levenberg-Marquardt backpropagation. The goal was 0.01 and the learning rate was 0.05. And perceptron input data corresponds to the 5 PCA components for each sample. Results and discussion. First, we have the electronic node response curves. Well, this is an example of sensors response to 40 types. Then we have the principal component analysis, and here we can observe a certain degree of clustering between the samples. So once clustering is verified, there is a high probability of successful classification of the samples by fitting the artificial neural network with the provided PCA scores. And finally, the classification results. The classification results and the values of accuracy, precision, sensitivity, and specificity are shown in this table. The shaded values correspond to the correctly classified samples. From the previous results, we can highlight the following. Electronic node curves. The sensors profiles have minimal variations between the sensors themselves and between each class. Nonetheless, the artificial neural network can identify the signal's internal pattern. Number 2, the principal component analysis. The PCA results show a certain degree of clustering between the samples, verifying the proposed clustering. And the classification results, the platform performed adequately since the records obtained provided enough information to be able to classify T. The classification model was proposed is valid for classifying T samples by groups according to their ingredients, and there is a greater selectivity to the components of samples classified as citric, sweet, fruity, and hibiscus tisane. Thus, the ingredients present in the samples can be identified, and the platform is suitable for the evaluation of complex samples. As conclusions, we have the use of commercial and non-specific gas sensors to tip volatile compounds can be useful in the characterization of these samples. The pressure-controlled generated stimulus is reliable for this type of studies, and the employed sensor array gives enough data for the proposed classification. Artificial neural networks model performs properly when they are fed with the information provided by the programmed stimulation cycle. The platform allows the real-time recording of olfactory stimulus. The record obtained analyses have shown good performance of discrimination, and the portable olfactometric platform developed can classify commercial tea brands, giving rise to future work related to the improvement of bioinspired systems for use in food analysis. These are the main reference of the work, our contact details, and that's all I have for now. Thank you very much.